Okay, we are going to start with chapter 5. In chapter 5, it is parallel circuits. So we are going to learn everything that has to do with parallel circuits. Chapter 4 was everything, all the characteristics with series circuits. In chapter 5, we are going to visit and learn the different applications of a parallel circuit. So resistors in parallel. Resistors in parallel are resistors that are connected in more than a single point. So both of their terminals are connected. Like in this case, we have line A or node A, and then we have line B or node B. What is a node? We are going to discuss node later in chapter 6, but right now we want to just define a little bit of what is a node. A node is where a point where we have several connections. So in this case we have 1, 2, 3, 4 connections. So this is considered a node. When we have several connections coming from a node, then we can analyze using nodal analysis. That will be a technique in chapter number 6. But here we have this resistor R1 is connected to node A and on one end, and to node B on the other end. So is the case for R2, so is the case for R3, so is the case for R4. So these 4 resistors are in parallel because they share both, or their terminals are connected to the same node. So they are connected to each other in more than one terminal. So if they are connected in more than one terminal, then they are considered to be in parallel. So what is a characteristic of a parallel circuit? A parallel circuit is identified by the fact that it has more than one branch or path for current, and they are all connected to a common voltage source. So we have our circuits right here. Why? Because we have voltage source, we have a closed path, and we have a load. So here we have this load, that load, that load, and that load. But what is important here is to know that here the voltage across all the resistors, it's the same. Why? Because this node is connected directly across from the voltage. You see, here connected to the positive, here connected to the negative. The same for R2, connected to the positive, connected to the negative. There is nothing in between here. So this jumper wire, or this line connecting these two, is drawn like this so that we just can see it clear. But in fact, this point can be squeezed into a single point where all these resistors are connected into a single dot. But that would be confusing, right, if we do that. So that's why we stretch it out like this, so that we say they all are connected across the voltage source. And if there is nothing between the resistor and the voltage source, then the voltage across R1, it is Vs. The voltage across R2 is Vs. The voltage across R3 is Vs. And the voltage across R4 is Vs. The difference here is that the current, it has different paths. The current can come here, split, some comes this way, some goes this way, some is going to come this way, the other one is going to continue this way, the rest is going to come this way, and some of it is going to go this way. How current splits is going to be depending on the value of the resistor. So the higher the value of the resistor, the less current is going to go through that branch. So current always looks for the smallest resistance. So if there was a short right here, a wire going from here to here, the source will burn out because the current will come here, it will try to go this way, but it'll see that if going this way through the jumper wire across here, it would be zero resistance. So then it would just go here. So it would bypass all these different resistors pathways. So it is important to understand that a parallel circuit is widely used because if one of these resistors is burned, the circuit can still functioning, not properly, but it can still functioning depending how important was the branch that burned out. Like we see these configurations in houses. In a house, you don't have a series circuit connection. Why? Because if some of the resistor burn, the whole house is going to run out of power. So we have different sets of branches. Like I don't know if you have experienced, sometimes only a section of a house has no power and the other house or the rest of the house has the power. So this is why, because a house, it is modeled as a parallel circuit. It's a little bit more complex. We'll see it later in chapter 6, but we can say that this is how a house would be modeled. So the voltage rule for parallel circuit. Like I said before, because all components are connected across the same voltage source, the voltage across each is the same. For example, the source is a 5 voltage source right here. 5 voltage source. That will be a volt. If we will use a voltmeter across all the three different resistors, we will see that the reading across each resistor, it is 5 volts. So the beauty of analyzing parallel circuits is that we always know the voltage. If the voltage source is given, we know the voltage across the resistor. We don't have to look for it. What we are going to solve for here, it is the current. The current is what we know. On the contrary, in a series circuit, we knew the current, we could find the current, and then we would know the current across all the resistors, and we will look for the voltage. In this case, if the voltage source is given, we would know the voltage across each different resistor. So how do we find a total resistance in a parallel circuit? Finding the total resistance in a parallel circuit is a little bit more complex than using or doing it in a series circuit. So see what literature says here. Parallel circuit rule for resistance. The total resistance of a resistors in parallel is the reciprocal of the sum of the reciprocals of the individual resistors. What does this mean? That means that if we have to find the R total, which most of the times we try to avoid this because it is very mathematically intensive, a lot of calculations, very easy to make mistakes. So we try to avoid that. But if we have to find it, if the question asks for a total resistance, and we cannot go using Ohm's law with the voltage and the current, then we will have to use this formula that says that the total resistance is equals to 1 over R1 plus 1 over R2 plus 1 over Rn. As many resistors as we have in the parallel circuits, that will be just keep adding them in this formula. So like I said, it's very math involved, so we try to avoid this, but we will do examples where you'll see how it can be done. So for this example, this is the first parallel circuit we have. So we have a voltage source, and then we have three different resistors connected in parallel, because this resistor is connected to that resistor and that resistor. So they are sharing one terminal. Now let's check on the other one. This resistor is connected to that resistor and to that resistor. So they are sharing the second terminal. So they are in fact in parallel. So how do we find? We will say 1 over 680 plus 1 over 1500 ohms plus 1 over 2200 ohms. We'll do the math and we'll get 386. That is a key point that we have to remember. Every time we are looking for a total resistance in a fully parallel circuit, the value of the total resistance, it will always be smaller than the smallest value of the resistor in the circuit. So here the smallest value was 680. We expect that the total resistance would be less than 680 ohms, and it was 386 ohms. So it follows the rules. So this is like a little easy way to check your answer and see if you are doing the math right. If your total resistance happens to be higher than the smallest value of the resistor in the circuit, and it is a full parallel circuit, only parallel connected resistors, then you did something wrong. So we are going to stop here.